In this video, you will learn to use Epsilon Integration Tool. This is a tool that provides you highly versatile integration procedures. Basically, Epsilon Integration Tool is a filter that can be applied on the top of several filters that we have discussed before. That Epsilon Aerodata, Epsilon Near Field, Epsilon Wave Drag, or Epsilon Poisson Solver. Independently of the filter that you have used, you can apply Epsilon Integration Tool that will allow you to deeper analyze the results that you're obtaining. In particular, you can put a single server plane at a specific position. Let's say at that position you have the distribution of a given parameter. For example, you have the energy distribution in this case, something we have discussed in the previous videos. Then what it does, this tool, is to integrate this distribution along the survey plane and gives you the integral value at that plane. So for example, this will give you the total energy, the total profile drag, the total vortex drag, and so on. In most of the aerodynamic analysis, what you really need is to perform such an integral in multiple positions all along the chord, all along the wake, in order to generate what we call the integrated distributed parameters, in order to see the evolution of a given parameter all along the axis. For example, what you're seeing here is the evolution of the profile drag all along the chord. For example, here the green curve. And this value, the total drag value, is decomposed into its energy and wave drag components. So you can do this kind of analysis to determine distribution of drag, decompose it, the evolution of lift, and so on. And what you see in this curve here, in reality, is generated by using multiple survey plane positions. So there is a tool that generates multiple planes and computes the integral at each actual position and gives you this kind of curves. In the case of 3D CFD data, you can use a planar survey plane. That's the standard survey plane. It's quite fast, and that's the standard method to compute integral data at a given survey plane. But Epsilon Integration Tool offers you the possibility to use custom-made survey planes. And this is quite useful for CFD data that hasn't the wake refined. We will discuss about that later on. And then you will have some experimental features that we're testing right now. For example, you can include the upstream part of the body. If, let's say, the plane intersects a given part of the geometry, well, we have a tool that allows you to retain the upstream part or the rear part of the body, depending on what you really want to need. And another experimental feature is to import custom surfaces so you can perform any integral on a given control volume. Then another practical application of this tool is to determine the span-wise drag or exergy distribution. Like this case, what you're seeing here is a given geometry and it's wake data at a given survey plane. And the red curve represents the integral value at each span-wise station of the drag density. So for example, at this section you have some certain density distribution, while this distribution is integrated, and the value is shown here with this point here. So this is quite useful for analysis of given configurations. The same tool can also be applied to determine the Maskell lift distribution, which requires a specific approach. It's the same approach in the sense that you use multiple positions all along the span to determine at each position the drag density. In this case, you determine the lift at each span-wise station. But the way you process data changes, so it's something specific for Maskell. And also you can apply the same tool, Epsilon Integration Tool, this time to Epsilon Near Field. So you can take the data available at the body surface and to determine the distribution of lift coefficient, distribution of total drag coefficient, and even the components. Another feature that's only available for 3D CFD data is what they call 3D mapping onto a plane. Basically, you start from a 3D volumetric distribution of a given parameter. For example, in this case, it's the lift momentum point by point. And what it does is put a survey line that crosses the entire CFD domain. And what you do is to integrate data all along this line, and the resulting integrated value is mapped into a point of a given plane. And of course, you do that for all the points that builds up the plane. So basically, you are condensing all the 3D distributed information into a plane. So this gives you a sort of cartography of the aircraft and its effect on the airflow. So it's quite useful to analyze complex geometries or even simpler geometries and to understand the physics with just a quick sight. So Epsilon Integration Tool, as I mentioned before, can be applied on multiple filters and allows making a lot of integration types. So it's quite complex, this filter. I showed you how it manages to achieve all these operations. The first step to achieve this objective is to generate survey points. What is that? Basically, let's say this is our geometry we want to study, or a 3D CFD case. You generate a sort of survey line composed of multiple points. Each one of these points represents the position of a given survey plane. So the idea is that the survey plane will place at this point, you will integrate data at that point, then you move the survey plane at this position, you will integrate data at that survey plane position, and so on. So at the end of the day, you obtain multiple integrated values all along this line, and the integrated values are assigned to each point. So I can actually plot the values that are stored in that point, those points. This shows you better what I have said before. I have the points that you can see here. Let's say for the last point, I generate a survey plane. At each point of this survey plane, you have a sort of density distribution. You integrate that density distribution, I obtain an integral value. For example, the profile drag at that survey plane is stored at that point, let's say this point here. Of course, all of these are BTK operations that are embedded into the Python code. You can modify that if you really want to. It's quite flexible and simple to modify the Epsilon code. Well, the first simple tool is to generate a survey planar plane. Basically, this survey plane is used for two applications. We slice the grid in order to perform surface integrals, and we clip the grid to perform volume integrals. Let me show you that. Let's say, when I say survey plane, I mean it's an implicit BTK operation. Basically, it takes the entire 3D volume and generates a function, a plane function. With this function, it slices the entire domain in order to generate what you see here, a slice of the entire 3D mesh. Of course, it's not only a mesh, but also the data that goes with it. And this is the way I generate a given survey plane. And the same implicit function of the plane can also be used to clip the domain. That is, I put my plane here, I split the volume in two parts, I delete one of the parts, I retain the upstream part, and this is used to perform some volume integrals. In fact, when you execute Epsilon aerodata, you will have some parameters that must only be integrated at the survey plane, and other parameters that must only be integrated in the entire control volume upstream of the survey plane. So this is achieved automatically inside the filter. Then another alternative is to use or generate an extruded survey plane. The previous case was a planar plane. That was the standard procedure. I always use that. But in some cases, you will need this kind of plane. I will show you that later in detail. But now let me show you how I generate such a plane. Basically, I start from the geometry. This CRM wing, I will show you later on how to download this geometry. Basically, you can use some standard tools that comes with ParaView that allows you to select some points of the mesh in an interactive fashion. You start picking those points all along the trailing edge in order to generate a sort of line. And this line is afterwards used to generate a plane function. And this plane function is used to slice the entire 3D cell data, and you generate your custom survey plane. In this case, it is a survey plane that it is not planar, but it is in contact with the trailing edge of the body. This is used especially when you have standard industrial CFD meshes. In those cases, you don't use to perform a wake refinement all along the wake downstream far away from the body. Instead, what you do is just to refine the boundary layer, and that's all. You really don't care about the wake. That's typical industrial procedure. And in those cases, if you put a planar survey plane, you risk of putting the plane far away from the refined region, and you have some numerical error, strong numerical error. So for those industrial cases, it's strongly recommended to use this approach, the custom survey plane. And of course, I can use this plane function also to perform a clip. So it generates a plane function customized that slices the domain and clips the domain. This plane slice is used to perform a survey plane integral, and the clip is used to perform volumetric integrals. Well, afterwards, you can perform custom integration surfaces. Basically, this is an exploratory feature. It's a new feature we are introducing. Basically allows you to import some STL geometries to compute the surface integral on closed surfaces. This is more a research aspect, not that useful for practical purposes yet. And then you have a way to compute the body plane intersection. It is also an experimental feature. Basically, let's say you put a survey plane across the geometry. When you do that, in the Epsilon V2, for example, what you get is the survey plane, but there's a hole in the survey plane. And this may generate some weird behaviors for the exergy components. So in order to cope with this problem, we were experimenting with this feature. Basically, we add the geometry that's generated in Epsilon near field, and this geometry is also sliced with this plane function, and the upstream part of the body is included into the survey plane, so we have filled this hole here with the geometry. And this has proven to be quite useful to obtain proper exergy values. Well, once I generated either the slice, either the upstream control volume, I can actually perform the integration. That's the really objective of my tool. So basically, there are 4 integration modes. The first mode is a survey plane. Basically, you put a survey plane at a given position, then integrates data, and the resulting value is stored at that point. So it is repeated for multiple points all along the core, so you can obtain distributions like the one we are seeing here that corresponds to the profile drag distribution all along the core of the geometry. Then you can use the same tool, this time all along the span. For example, we have here a coarse mesh of a given geometry. There is a slice of the wake. Then let's say at a given span-wise geometry, I put a survey plane. This survey line here contains a given distribution of a given parameter. What I really want to do is to integrate this distribution, and then the integrated value will give me the profile drag at that span-wise station. Of course, I do the same for several stations all along the span, and the resulted value can be plotted in order to obtain the span-wise distribution of the profile drag. And this is what I get here. This is the same wake that has been integrated in multiple points all along the span, so I can visualize the local profile drag at each station all along the span. Then, for the case of Maskell lift distribution, the procedure is quite similar, but you have to take into account the physics. Indeed, for the case of lifting line, you know that the wing generates at a given station certain circulation. Then, if you want to obtain the circulation at that section, but measuring that at the survey plane, you have to measure circulation starting from this spanway station towards the tip of the wing. So you have basically to define a region that encloses the wake starting from this specific spanway station going up to the tip of the wing. So basically, if I want to compute, let's say, lift at this section, I'm not only using this station, but I'm also using all the surface starting from the station to the left in this case. And this is what you do inside the tool. You don't actually see that because it's done on the background. So let's say this is the wing, this is the wake of the wing, and I want to obtain the lift distribution by Maskell. Lift distribution by Maskell is given by this expression where you have the actual vorticity inside the wake and its span-wise coordinate. Basically, let's say I want to obtain the lift distribution at that position corresponding to this point here. Well, based on what I said before, in order to compute that, what I have to do is to integrate this quantity in this region here. So all the quantities lying in this area are integrated from the station outwards, and the resulting integrated value is assigned to this spanway station, and it's plotted here. Then, if you apply the filter to the near field, epsilon near field, you can obtain lift and drag distributions. So again, you start from the geometry that's provided by epsilon near field. You apply the filter and it will slice the geometry at given spanway station. And for each one of the slices, it will integrate values and give you the local integrated values all along the span of lift and drag. You can actually see here in this image a slice, and it's also, I incorporated the surface normals just to illustrate that the normals drive the sign of the lift or drag that is computed by epsilon near field. And the last feature provided by Epsilon Integration Tool is 3D to 2D mapping. As I mentioned before, basically you are taking the entire 3D volume data, you integrate that into a plane, you make a sort of mapping. We will understand that better afterwards. Basically, the plane what you are seeing here is just a rectangular plane with a mapped grid inside. You can control the quantity, the amount of points all in both axes. And basically, for each point of this mesh, you put a line of this type that surveys the entire 3D volume all along this line. And this data all along this line is integrated and assigned to the point P, that is to one of these points here. And of course, the survey line is swept all along the two axes to cover the entire plane. So at the end of the procedure, you obtain a sort of mapping of the entire 3D volume into a plane. And this is quite practical for analysis of complex configurations. Well, the output of the filter is BTK poly data, simply because we have a surface at the end of the analysis. Basically, all what we have discussed before can be found at the interface. The interface, as you can see, is quite complex. There are plenty of parameters to interact. So we will understand better all what we have discussed before in the practical session that we will tackle in the next section. Well, now we will see how to use Epsilon Integration Tool. For this application, we will use open data available at our website. So go to the Epsilon site, here in open data, CFD data. And we will use the first case. This is the 2D subsonic case of an AK-12 airfoil and corresponds to an angle of attack of 10 degrees at Mach 03. So I let you download the file, open it in ParaView, and then you have to execute Epsilon Aerodata, as explained in the previous video. So I have already performed that before. So I have here the case. I will change that to 3D to facilitate the manipulation. And I have all the fields already computed by Epsilon. And now what I will do is to apply the filter that we have just discussed. And the filter is this one, Epsilon Integration Tool. As you can see, there are plenty of parameters to modify. So it's organized in order to be systematic from the top to the bottom. We'll start first with the integration tool parameters. The first thing that you have to define is the input module. In my case, I have to say that I am applying Epsilon Integration Tool to Epsilon Aerodata. So here I have to declare the input filter where it is applied. Of course, you have other options, but it's very important to declare where it comes the input data. So in my case, it's Epsilon Aerodata. Then you have to indicate the integral type. There are multiple modes. We will see that each one of the modes all along this tutorial. We'll start first by the simplest mode, that is the single survey plane. And then this button, select action, as you can see, contains multiple actions. It's the button that we will use a lot, so we'll try to have it in hand. And it's also organized all these actions here in a systematic manner. By default, always visualize what you are selecting. In my case, I want to perform a single survey plane, so the first thing that you will do is to visualize the actual survey plane. Let's apply that by default to show you what it generates. As you can see, once I apply, it generates here a line. So basically, it has generated a survey plane that is normal to the upstream flow direction. As I mentioned, this CFD case is a simulation of an angle of attack 10 degrees. So the plane is inclined by 10 degrees. Indeed, all the parameters concerning this survey plane are here in the survey plane sector. This option, input data, is already a survey plane. It will be used in 3D cases. We will see that afterwards. So let's ignore this for a while. And in plane shape, for 2D cases, it's only planar. This extruded curve can only be used in 3D cases. So let's stick to planar for 2D cases. And then you can define the plane normal, or you can use some specific values. For example, the plane normal by default is perpendicular to the aerodynamic x-axis. This is what you are seeing here. But you can choose other options like user-defined, and you can set the normal that you really want. For example, I want to have the survey plane normal to the mesh x-axis. These components are expressed in the mesh reference system. So if we apply, you can see this time the plane is normal to the mesh x-axis as established here. Regardless the inclination of the plane, the integrated values will take that into account, and you'll obtain the same drag value and the same lift value and so on. So the inclination is taken into account for the integration, basically. But it's a standard practice to use the survey plane normal to the upstream flow direction like this, so I will stick to this. The only thing that I will do is to change the actual positions. By default, it's placed at the origin. I will put that downstream, let's say 0.5 meters, just behind the trailing edge, like that. And the option clip weight region, it's also a feature that I always use it, especially in 3D cases. You can also use that in 2D. I will show you that later on, but basically, if you have here an Epsilon Aerodata, you can visualize the fields. For example, let's say this arms CD. Basically, let me change the scales. What you're seeing here is the drag density at each point of the domain based on the arms exergy equation. So if you put this survey plane here, you will see that the drag density has a given value. So what you really need is to integrate this density all along this survey plane to obtain the profile drag at that position. As you can see, this formulation, the formulation for arts, is distributed on the entire domain. So you have non-zero values all on the entire domain, even inside the wake or outside the wake. But there are other formulations that are wake reduced. Let's say method profile drag, like this one, where the drag quantity is this time reduced to the wake, as you can see here. Green is zero. It's zero all outside the viscous region. It's only non-zero inside. So in this case, it's useless to integrate values outside the wake because it might only add some small numerical error that in a very large surface may induce some significant errors. So in that case, instead of integrating data on the entire server plane, you just integrate data just across the wake. And that's why you have here in Epsilon Integration Tool the possibility to clip this wake region. Well, now you have defined your server plane, you can keep going. The next section of the interface concerns the integration variables. When you visualize the server plane, as you see, the server plane is white. White means that it is in solid color, and as you can see, there are no variables to color the distribution line. What happened? Well, it happens that you have to select a method. Basically, Epsilon Integration Tool will integrate what you're seeing here. If there are no variables, it will integrate nothing. What can I do in order to make appear some variables here? Well, what you have to do is to activate the variables that you really want to integrate here. For example, in my case, let's say I want to integrate this quantity, method profile drag. I have to go here to the farfield method. By default, it's none, so none of the farfield methods are integrated. You have to change that. You have to either select all the methods or you select one. In my case, I'm going to select the method. And if that's okay for you, when you apply, this time you have some parameters to visualize. Let's say the profile drag. And as you can see, the line has the same color as the background. And you can do the same for the other quantities. Now you are ready to keep advancing in your select action. As I mentioned before, select action indicates the procedure to follow in order to achieve our objective, that is integrate data at a single server plane. What we are doing just now is to visualize a given server plane, that is this, and we are visualizing also the parameters at that server plane. We can also visualize the control volume. As I mentioned before, the implicit plane function is used to slice the domain in order to generate the server plane, but it's also used to clip the domain in order to retain the control volume lying upstream of this plane position. If you can visualize that, you can visualize that with this option, visualize control volume. When you apply, you will obtain, let me hide Epsilon Aerodata. Okay, that's what you get. That's the output from Epsilon Integration Tool. As you can see, it has taken the data coming from Epsilon Aerodata. It has defined a given server plane position, and this implicit plane function has been used to clip the domain and to retain the upstream region. Of course, again, you can clip and retain only the wake of the part lying inside the wake. For example, if you go here to clip wake region, select this method, this quantity that I'm seeing here, method profile drag in this case, and define a clip value. This time it will retain not only what lies upstream, but also what lies inside the wake. I just deactivate that. And now that I'm happy with that, I'm happy with my server plane, I am happy with my control volume, I can finally integrate variables. So let's go for it. And as you can see, the only thing that you will see for this case is just a point here. Indeed, the integrated values cannot be visualized on the interface. You have to go here, click on the plus button to generate a new layout. Then you go to here, spreadsheet view. Make sure that you are selecting Epsilon Integration Tool here, in point data, and you have here the integrated values. For example, profile drag for this case is 128 drag count. An important thing about this is that this quantity has been integrated at the surface. How this we can know that a quantity must be integrated at the surface or the volume? Well, this is declared in the previous filters. Let me show you that. I will go back to Epsilon Aerodata. In Epsilon Aerodata, as you know, there are plenty of parameters that you compute inside the filter. And if you go to the new layout, spreadsheet view, in Epsilon Aerodata, but this time you go to, instead of point data, you change that to field data, you will see that there are two arrays, one called array and other called array integration. Basically, this is a list that I generate inside Epsilon Aerodata, and basically I declare here each variable if the way it must be integrated. For example, I declare that this quantity must not be integrated, so when apply Epsilon Integration Tool, it will ignore this quantity. Instead, other quantities, for example, velocity, can only be integrated at the server plane. But there are other quantities that can only be integrated on the control volume. For example, let's here. Phi is the effective dissipation. So effective dissipation will give you the amount of power that is dissipated through the viscosity. And this can only be integrated inside control volume. It's a volumetric integral. And so I declare this in this list. And then Epsilon Integration Tool goes, read this list and say, hey, this quantity must only be integrated in the control volume. So it doesn't perform a double integral. It's just integrate in the control volume, but not at the server plane. And the same, exactly the opposite for this quantity. It can only be integrated at the server plane, but it is not integrated at the control volume. So this information is transmitted downstream. It's generated at each filter, and then Epsilon Integration Tool should read that information to know what you have to integrate and so on. So that's all for a 2D case with a single server plane. Now we can go forward and perform a complex operation. Let's say I want to compute the distribution all along the chord of this quantity, the profile drag. So we can do that. We're still using Epsilon Aerodata, so input module, I will not change that because I'm still applying Epsilon Integration Tool to Epsilon Aerodata. But this time, the integral type will be changed. Actually, we're using single server plane. We'll change that to sweep server plane. And as you can see, we still have this button here, select action, with other options this time. The first option is always a visualization option, so you don't perform heavy computation. It's faster to visualize the first step. Let's apply it as it is to take a look what we are doing. I will change the size of the line. Here you go to styling, line width. You can only increase the line thickness, so you can better see that. Even the points, let's put 5, maybe higher. Okay, so you can better see the line. Basically, I'm generating a line with multiple points, and each one of these points, I will put a server plane, and then I will integrate data at that server plane, and the integrated values will be stored in this point. So at the end of the day, I will be able to visualize the distribution all along this line of a given parameter that has been integrated at all those positions. So I go back to my filter here. We have established that. This part is okay. Now let's modify this section concerning the server plane. The first option is to define the plane shape. You have always two options, but for 2D cases, you can only use planar. So let it here as it is. What you can change is the plane normal. By default, the server plane is always perpendicular to the aerodynamic x-axis. That's by the standard conventional approach in aerodynamic analysis. So this is the default value, but you can change that. You can use user-defined as explained before. And then you can modify the sweep axis. As you can see, the line is inclined respect to the chord line, and the angle of 10 degrees. In fact, it has taken the information coming from Epsilon Aerodata that says that the airfoil is studied at 10 degrees angle of attack. So the sweep axis is by default established along the aerodynamic x-axis. So that's why it is inclined. But you can establish this line aligned with the chord axis. So here you have to change that to the mesh x-axis. If you do that, this time the line is aligned with the chord of the airfoil, which is more practical for this kind of visualizations. Then you have to define the initial position of the line here and the final position of this line here. By default, it's established always between 0 and 1 meters. I will modify this a little bit. I will say that, let's say, 0.5 meters. So you can change the length of the distribution and the amount of points of distribution here. Let's say 20. But by default, I suggest you to let that really large, something like this. So you can perform a sweep all along the way to have a first idea. With few points, 20 is way too much. Let's say 5 points to a first guess to have an idea how it looks. And then you start increasing because sometimes the integration may take some seconds. It's better to perform a sort of iteration to feel how it evolves the core. I will show you just in a second. So let's start something like this, better 10 points. Then, as I mentioned before, you can clip the wake if you desire. I will not do that just to show you the example, but you can clip. Again, you have to define the parameter and the clip value. Then, very important, do not forget to activate the variable that you really want to iterate. By default, none of the variables are activated, so you will not iterate nothing. It's very important to be aware that you have to select something before iterate values. In this case, I will keep iterating method profile drag density. Now, I go back here to select action. The first step was to visualize the sweep line. I'm happy with that. I can continue. And so I can visualize the server plane. What it does is to take the point roughly at the middle of this distribution line, and it will show you the server plane at that position. So it is. As you can see, if I go back, it takes this point here, and at this point, it will show you the server plane. I go to the second step. So this is just to confirm that the plane is actually normal to the aerodynamic axis. That is what I have defined here. If you want, you can change. You can use, let's say, the mesh x-axis. But I go back to aerodynamic axis. This is just a visual confirmation, so that's all. And you can also visualize your control volume. If you apply, let me hide here our data, you will have the upstream control volume lying in front of the server plane position. Now that I'm happy with that, I'm happy with the server line, with the server plane, and the control volume, I can finally perform the automatic integration. So I go ahead. It will take some seconds, but it's here. Here what I have is a line with multiple values. They are colored by the profile drag here. You can visualize that better. Let's close this and close this. Let's generate a new layout, spreadsheet view. And you can see I'm visualizing the Epsilon Integration Tool, its output. And as you can see, you have the 10 points that have defined. You remind, I put 10 points all along the line. And for each one of these points, I have the integrated values. You can see, for example, that profile drag, it changes all along the axis. And even you have here in points the coordinates x, y, z. So all along the x-axis, you have the coordinate and integrated value. If you activate again Epsilon Aerodata, there's a way to visualize this, very practical indeed. You go here, Epsilon Integration Tool, and you go to Filters, Alphabetical, Work by Scalar. And I will take the parameter that I really want, that's this one, method in profile drag, and I will warp vertically this line proportional to the local integrated value. So I will warp this all along the y-axis. Let's try it like this. It's way too small. Let's say 10. Okay, you start seeing that it start moving. I put my reference line here. I will change the color so I have some background. Same here. This line is colored Let's put in solid color. Let's change that to black. And let's increase the line width. Okay. This is the integrated value all along this line. Of course, this line was quite coarse. So what I will do is go back to Integration Tool and increase the number of points. Let's say I will put this line closer to the body and increase the number of points 20 and launch that again. It will take some few seconds and start giving me the line. I can put that even upstream, let's say minus 0.5 and increase that to 40 points. Takes some seconds. Okay, it starts taking shape. I can close that, let's say 0.2 to 0.8. I will increase that to 80 points. Let's keep digging. It will take, of course, a bit more time because we are integrating data at 80 server plane positions, but as you can see, it starts giving the typical distribution all along the chord. Here's a small issue. I will explain in another video how to fix this problem. This is related to the upstream reference value, that's all. Basically, this distribution is okay, but it's shifted downwards by this quantity. You have to shift it back upwards. There's a way to solve that because it's related to numerical errors. At this point where I'm not trying to explain the physics and how to interpret the results, I'm just trying to explain how to use the interface. So this is what you have to do to obtain longitudinal distributions like this of any other parameter. I go back, I will do exactly the same this time, but I will use, for example, I will close here, far field, let's say known. I will go to Exergy, I will select arms, and when apply, it will take a bit more time because there are more parameters to integrate and some of them are volume integrals. That's I really want to show you right now. And it will show you that epsilon v3 is far more powerful than epsilon v2 concerning the integrated data. For example, here you have all the points. As I mentioned, there are 80 points, so you have here 79 plus the 0.0, you have 80 points, and at each point you have the integrated quantities. Again, I can work by scalar. This time I can select RCD, that's drag. You can see that you have some weird distribution. It doesn't matter, we will not analyze that. But the interesting thing of this is that this quantity, for example, Fe, you will see later on that is a volume integral, whereas other quantities like, for example, this one, CD, requires a surface integral. So epsilon automatically recognizes that this quantity must only be integrated at the surface, whereas this one must only be integrated at the control volume. And this has been achieved for any server plane position that we have defined. And this is it's quite efficient and time saving compared to epsilon v2, so this is a major advance. Well, I will delete my work by scalar. I go back to Epsilon Integration Tool. We have seen the first mode, that's single server plane, the second mode, that's sweep server plane, and we have two other modes that are span-wise distribution and 3D to 2D mapping. These two options cannot be applied in 2D cases, so now I will load a 3D case and I will show you these applications. Well, this is the 3D case that we will use for the study of the complementary tools. Basically, it's the 3D case that's available at the open data in our website. It's the rectangular wing with omega 12 airfoil at an angle of attack of 10 degrees. I have already implemented Epsilon aerodata and I have extracted the surface by using Epsilon airfield. So now I'm ready to keep going. I will go back to Epsilon Integration Tool. I will select Epsilon aerodata. I will make sure that it is in blue, so it is the active element, and when I apply the filter, it is applied on the top of Epsilon aerodata. Input module, it's still Epsilon aerodata, so I will not change that. Integral type, this time we will change that. We have explored single server plane, sweep server plane, and now we will study the span-wise distribution. Again, this button is very important, select action, because we will use that multiple times for multiple sequential actions. The first one is to visualize the server plane. before clicking on apply, I will parameter the survey plane. The first option is to indicate if the input data is already a survey plane. This is mostly used for example, if you are performing a wake survey with wind tunnel data, the input data will be already a survey plane. You don't have really a 3D domain. So you have to click on here for that cases. But for CFD, you already have the entire CFD domain, so you don't really have to use this option. And this is also required, for example, if your input module is the Epsilon Poisson solver. If you remember, Poisson solver is, we solve the Poisson equation at the survey plane, so the output of the Epsilon Poisson solver is a plane data. And in that case, you have to click here. In my case, again, it's a 3D domain, so I have to generate a survey plane. The plane shape, again, it will be planar. We will talk about the extruded curve later on. Plane normal, I will stick to x-axis, that's the standard procedure. You can also define other plane as before. And we'll put the plane just downstream, let's say 0.8 meters, that's almost 1/4 downstream. Let's visualize the survey plane. It will take just some few seconds pass because it's quite heavy mesh. So as you can see, it generates the survey plane. It has started from the entire domain that is provided by Epsilon Aerodata. It has generated a BTK implicit function, and with that function, it has sliced the entire domain. And I can actually visualize data. Sorry, I go back here. As you can see, there are almost no parameters to visualize because, again, you have to indicate that on the filter. Make sure that you're an Epsilon Integration Tool, and here, down below, you have to declare what you want to integrate. Basically, you will integrate what you visualize here. Here, there are no parameters coming from Epsilon Aerodata, so I have to activate that. Go to here, integration variables, and this time let's integrate, for example, far field, select, and again, we will activate method. When you click on apply, it will take again some few seconds to generate the survey plane, but this time I will have some parameters, and let's visualize the profile drag, for example. You can actually see the wake on the vortex here. Again, what you see is what you will integrate. So now that I'm happy with my survey plane, now that I'm happy with the quantities that I want to visualize and integrate, I can keep going. We will tackle this time the span-wise distribution. So the first step was to visualize the survey plane. But we don't want to integrate data, all this data at this survey plane. What we want to do is just to retain the wake and at each span-wise position integrate the density in order to obtain the span-wise distribution of the profile drag. Well, we will go to the next action, that is visualize the span-wise sweep plane. But before clicking on apply, we have to parameter this line, the sweep lane. So you have to go here, the span-wise stations. You have to define a survey line that lies all along the span. And this line, you have to define the axis. By default, it's the aerodynamic y-axis. So it will be pointing in this direction. We'll start with 10 points. It will start in one, let's say 2 meters. Let's click on apply. It will take some few seconds. Okay, here's the line. We will increase a little bit the point size and the line width so you can see that better. This is the line. Basically, it will take the wake. For that wake, it will take survey lines positioned at each one of these points. And at each line, it will integrate data. So, the first step, we visualize the survey plane. Now we have visualized the span-wise sweep plane. And now we can visualize the integration sections. So if you click here and you click on apply, it will take the point at the middle of the distribution. It will generate the survey line that intersects the entire plane. As you can see, it has taken the survey plane and one slice of that survey plane, so that gives you data all along this line with density of this variable profile drag all along this line. And you want to integrate that and assign that to the point. So that's the next step. Visualize integration surface. In my case, I don't have to click because this is more for Maskell method, and we are not integrating yet. That I will show you that afterwards. So yes, exactly, it gives you an error because we haven't activated Maskell. We will do that later on. First of all, in order to accelerate this thing, we go back to Visualize Survey Plane, and this time I'm gonna clip wake region. I will clip by method profile drag. Let's put a clip value of 0.1 and let's take a look at this. Takes just a few seconds, but it's taking the survey plane only at the wake. Okay, perfect. And this is the quantity that I will integrate. So the integration will be faster. So I'm happy with my survey plane. I'm happy with the span wave sweep plane, the integration sections, and now can go finally to the automatic integration. So let's go ahead. It will take some seconds. Basically, what it is doing is slicing this wake, and for each slice, it's integrated the values. It's here. We have the span wave survey line with integrated values. You can actually see it here if you select Integration Tool. You have the 10 points all along the span, and for each position, you have the profile drag distribution. So let's go back here. We'll try to visualize it in different manners. The first alternative to visualize this data is the one we haven't used yet. This is by using plot data. I go here, I go to filters, alphabetical, plot data, here. If you click on apply, it will generate a new window. You have to define the x-axis here, and I will use the points Y position, and I will just only visualize the profile drag at this point. Why? So the wing has a span of 1.8 meters roughly. So it starts from 0 to symmetry plane, 1.8 or 1.75, so I'm not wrong, is the tip. And this distribution, of course, is quite coarse. I have to increase the number of points all along the span. So let's go for it. Let's go back to Epsilon Integration Tool. We will positionate the first point. As you can see, it's 0 because it lies just outside of the wake. I will have to put that a little bit inside the CFD domain. And then the number of points, let's say I will increase to 20 just to see how it looks like. You have to wait some few seconds, and this the iteration will be updated as well as this plot here on the right hand side. And now you start having something more classical. This is the span wave distribution of the drag density, and as you can see, there is an increase of drag around the vortex region, and then you have the profile drag distribution typically of the viscous effect. So you can keep going, keep increasing the refinement in order to improve this resolution here and the number of points here. I'll let you play with that. It's just to demonstrate how to use that for that case. So this is one of the approaches to visualize the distribution. You can actually see the value and the positions like in the typical plot. There is another way to visualize data, and it's warp by scalar. This is quite practical indeed. So we go to filters, alphabeticals, warp by scalar, and this time I'm going to select the profile drag, and I will warp this line vertically proportional to the local drag density. So vertically is along the z-axis. Okay, it's good. And let's try to see. I think it's too small. Let's increase the scale factor, maybe like this. Okay, and you have roughly the same plot. The difference that this time is overlapped on the top of the wing. You can improve that. You can go, for example, here below, and you can activate this option, data access grid, that will show you the coordinates and this value. Of course, keep in mind that this vertical axis here is in reality 50 times the local value. So the value here, this coordinate is not 0.3, it's in reality 0.3 divided by 50, the real value. That's why the other layout, the plot data, will give you the true value, whereas this kind of plot usually use it just to visualize in a qualitative manner to visualize the distribution, but I don't use to plot the real value with ParaView at least. Well, now let's go back and let's try to implement the Maskell approach here. As I mentioned before, we are using the span weight distribution, and we have applied all these approaches, but there is one we couldn't visualize, that is this one, iteration surface, and that's because we haven't activated yet the Maskell method. So let's scroll downward, and let's select this time, besides method, let's select the Maskell method. Let's first visualize the survey plane, and I will show you what are going to do. Just a few seconds that generates the survey plane. Okay, it's done. And I have method parameters, but I also have some Maskell parameters. In particular, I have Maskell lift that gives me at each point the lift contribution. So this time, as I mentioned before, I will take at each position the area lying outside of the span weight station. So when now I can visualize the sweep line as before. I can also visualize the integral sections, but I can visualize the surfaces. So let me show you that. It will take the point lying at the middle of the span weight sweep line. It will clip the wake at that region. As you can see, it has taken this point here, but it's taking the wrong part of the wake. It should take the part lying on the outboard part. This can be easily corrected. You go here downward, invert domain clip, and if you apply this time, it should be corrected. And that's why we visualize everything before applying the integration, because now I can effectively confirm that this is the zone that I really want to integrate. I'm happy with this, and now we can keep going and perform an automatic integration. Let's go for it. It will take some few seconds, and basically it will sweep the span weight station all along the span to generate the lift distribution. So let's verify here, spreadsheet view. At each one of the points, I have the Maskell lift distribution. I will again plot that visually. Let's say filter alphabetical plot data. And again, I will select the Y component, and I will only plot this time Maskell lift. So this is a lift distribution, but only limited to 1. It's quite small. I have to reconfigure that. I will put that 2 meters, and let's say 50 points. Let's launch again. It will take some few seconds. We have 50 stations, but we will update the integrated values and also this curve here. As you can see, the curve this time goes from the symmetry plane at 0, y coordinate. It ends up here. This is the wingtip, and you can actually see the lift distribution all along the span. And outside of the wing, of course, there is no wake, so there's no lift here. It's 0, and so this is how you use the wake data to obtain the lift distribution with Maskell. At this point, we have discussed all these 3 approaches. There is a method that we haven't discussed yet, that is this, the 3D to 2D mapping. And the other feature that we have to check is this one, extruded curve. For these cases, I will use another 3D case that you might find in our website. So if you go to our website here in Epsilon, this time you won't find this in open data. Instead, you have to go to documentation, meshing technique. Here you have some tutorial of how to perform this kind of high-resolution wake data if you want to study wake or perform any type of wake analysis. But besides that, what I really want to use is this case, CRM wing. It's the case that you're seeing here with swept wing. And I will use this wing because its geometry allows me to better explain the features of that I want to explain from Epsilon Integration Tool. So I'll let you download the file and we will open that with execute with Epsilon Aerodata and we will analyze that. Just keep in mind that this case, this wing, is just a coarse mesh that is not fully solved. So it's basically just to demonstrate the features of the Python code, but it will not provide accurate physical solutions. So it's a coarse mesh just for demonstration applications. And that's why it is not included in open data. The data that you will find here will provide accurate values, whereas the data that you are here is just qualitative. So keep that in mind. Well, I have opened the file. It's the CRM wing. I have executed Epsilon Aerodata, and I also have extracted the surface by using Epsilon Nearfield by using these parameters here. I'll let you reproduce that. Basically, now that I have my swept wing, I can implement the lacking methods that we haven't verified yet from Epsilon Integration Tool. So let's click on Epsilon Aerodata. Let's go to Epsilon Integration Tool. And this time, I have as an input module Epsilon Aerodata. We let that as it is. Integral type, we're still in single survey plane. Select action visualize survey plane, but this time the survey plane will not be planar. Let me show you first why I will need something that is not planar. Let's start with the planar. Let's put that, let's say, the 55 meters downstream. And basically what I have is the 3D domain. This is the entire 3D domain. And it has been sliced just downstream of the wing. The output, if I show you with surface with edges, you will see the remaining of the envisaged region, and the viscous part is relatively well refined. I remind you that this case is a coarse case. It will not provide the accurate values, but basically it shows you that in the wake, usually we refine it, but such a refinement is not available in industrial meshes. In industrial mesh, you will just only refine the boundary layer, and that's all. You have a coarse mesh usually in this region, and the fact of having a coarse mesh will mean that you will not have any parameter. Just let me show that in detail. I forgot to activate some parameters. Let's go back to far-field method. Let's select method again. Let's apply. Let's visualize the profile drag. And this quantity from 0 to 0.1. Let's say we visualize something. We cannot visualize nothing. Okay, that's better. As you can see, this wake lies roughly inside the refined region. But in an industrial mesh, as I said before, this refinement region will not exist, and all the information lying shedding from the boundary layer all along the wake will suffer a massive numerical dissipation. The information that you will have here will not allow you to compute drag in a correct manner, because basically data will not be physically reliable. So in those cases, using a planar survey plane is not an option. What you would like to do is to have a survey plane that is attached to the trailing edge, because you are sure that at the trailing edge the boundary layers were resolved, so your wake data at that position is very well resolved as well. So what you can do to do that? Well, it's actually quite simple. First of all, you have to change this from plane shape planar to extruded curve. And as you can see, there are multiple options. You have to load a curve. But before loading the curve, we have to generate this curve. Let's apply it. So this line will disappear. And as you can see, the surface generated by Epsilon Nearfield contains the surface but also the mesh. So what we will do right now is to use these tools, the interactive tools provided by default by ParaView. In particular, we will click in this option, select points on. Basically, it allows you to pick some points. Let's click that again. If you click, you can select points of the mesh in an interactive manner. And let's say you have selected these points, you can add extra points. You click down on that again, you keep adding, you can delete what you have selected. They are quite useful tools, and we will use that very often in our analysis. We'll see that later on in a specific video. But now I just want to generate a line lying along the trailing edge of the geometry. Well, you can do it in two ways. One way is, as I mentioned before, you click on the plus button to add the selection, and you click here and select points on, and then you have to select one point at a time, but it's quite difficult in this kind of meshes because, as you can see, I have selected multiple points, and this is not what I want. I really want just to select one point here, so I will delete this. The simple way to that is by using these options over here, interactive select points on, this one. So basically, you enter in interactive mode, click on OK, and as you can see, as I move the mouse cursor, it will sweep the point and shift it to the closest mesh point to the point, my mouse pointer. And this is quite cool because I can just click here, I will select this point, click here, I select this point, and I keep doing that all along the span. So I'm marking points all along the trailing edge. It doesn't matter if I forget a point, let's say hey, I want to extra point, let's say here, I can go back. It doesn't matter the order yet, I will reorganize the points afterwards. Let's add another point here. And that's all. I'm happy with this. Now I have to do is to extract those elements. So you can go here, filters, alphabeticals, extract selection. And what I have are the points that I have just selected. Just I want to get out of the interactive mode. I press escape. Now I don't see this violet point. And I just have here in the extracted selection the points that will allow me to generate the survey line. So what I have to do is to save these points. I make sure that extract selection is in blue and go here, save data. You will say that, I will save that in my desktop. I will put, I will save that as a BTK. We'll try that. Let's save that span-wise line as it is. And now I will go back to Epsilon. Let's hide this. Let's eliminate again the Epsilon airfill. And the points that you have here can be deleted, no problem. And go back here to Epsilon Integration Tool. You have to load the curve. Just click span-wise line. Then you have to sort the direction. As I mentioned before, it doesn't matter the order of the points you are picking, but then once you load this file into the code, you have to sort it. In this case, the points are mostly aligned with the y-axis, so I'll retain this, but you have other options. I will retain this by default. Let's visualize the survey line. It will take some few seconds. Voila. Basically, it has taken the line that I generated from the trailing edge points. This line has generated a BTK implicit plane. Based on that plane, I have sliced the entire CFD domain. What you're seeing here is the result of that slice. You can actually see that it generates a custom surface. It's no longer planar, it's inclined, and it follows the trailing edge of the geometry. So it fulfills our need, and as you can see, this slice contains the boundary layer refinement, so it will provide accurate solution for industrial CFD meshes. And then the rest of the procedure is same as before. Now we are visualizing just the solid plane. We can visualize the control volume as well. Just wait a few more seconds. It will retain the entire volume upstream. Now as you can see, just hide this geometry. Now you can see that it retains the entire volume, including of course the wing. This is the part of the domain that will be integrated. And then you can go ahead and integrate variables as we shown before. So this is how you generate a custom server plane. At this point, we have discussed, all these three options: single server plane, sweep server plane. We have shown that for the 2D case all along the chord and for the 3D case all along the span. And we have visualized the span-wise distribution, these two options. And the option that we haven't studied yet is this one, 3D to 2D mapping. And I will use this test case as well to demonstrate that. So I will delete this. I will delete the extract selection. I will show you the wing. Now I will apply again Epsilon Integration Tool. Again, I am applying Integration Tool on the top of Epsilon Air data, so I retain this here. Integral type, this type will be 3D to 2D mapping. As a default action, you have always the visualization, so let's go for it to see what it generates. It has generated, it's very small here, but it is actually a plane. Yes, you can see that the plane. It's not just a plane, it's a mesh. Voila. What you have to do is to put this plane under the wing, first of all. So we have to define the normal of the plane. The normal by default, the x-axis. I want the normal be the z-axis, so I can change that. You have multiple options. I will put the mesh z-axis. So this time the plane is like this, like I really want, but it's quite small. Let's increase its size. Let's say that 50-50, just to take a look at this. Okay, it's taking a good shape. To position it, you have two axes, this I and J axis. You have to check which one is which. Let's see. Okay, this is the x-axis. And it will start, let's say, at 30 meters to 60 meters. Let's take a look at that. Okay, it's not that bad. And in the span-wise position, it will start from minus, let's say, -5 to -50. And I have my plane almost placed under the body. Okay, I'm happy with this. We'll just make a preliminary test. The plane is roughly well placed. Now I can go beyond. I have to perform the automatic integration. But do not forget, you have to indicate what you want to visualize and what you want to integrate. In this case, we'll try to visualize Muscle lift. That will be simpler. Sorry, moment to conservation method. It will be easier. Let's apply it. You cannot visualize anything yet because you have to integrate. So perform automatic integration. It will take not that much. Momentum lift. So basically, what are we doing is taking each point. We have taken a survey line normal to this plane that crosses the entire CFD domain. And all along this line, I have integrated data, and the integrated value is mapped at this point. And it has been made for all the points lying at this plane. So now that I have a first guess of where is placed this region, I can keep improving the plane and the refinement. So for example, here I can shift it downstream. Instead of 20, you can say, let's say 25. And span is way too far away. Let's put it 45. And let's increase the number of points. Let's say 30 here. And let's try to take a look how it looks like. You can see that's getting better and better. You have to keep refining and keep changing the position. I let you play with that. And keep in mind this 3D case is quite coarse, but when you have a highly refined CFD domain, it will take a significant amount of time to perform such an iteration at all these points. So my suggestion is to start with the coarse mesh and start first figuring out the position of the plane, and then once you are happy with the position of the plane, you can start increasing the number of points. Once you are happy with that, if you really want to wait, you can just put a lot of points and let it run maybe half an hour, 15 minutes. And at the end of the process, you can even activate this option, save output in BTP. So basically, once it finishes this computation, it will save it automatically as a BTP format. So this is quite good. For example, if you have a highly refined with hundreds of millions of cells and you want to do a very refined resolution of the mesh, you can let that running during the night, and at the end of the process, it will save the output here. So that's all concerning Epsilon Integration Tool. You have checked all the options, so thanks for watching.